Hey everybody, this is video 5 in preparation for the unit test on interactions coming up this week. I found my pointer. So now you don't have to look at my fingernails or a pen. On the last video I was talking about calculating rate. It was Friday, I was tired, and I know we had calculated rate for the mean rate for the duration of the experiment, and it came out to be about 37 or 38 cells per hour. And then towards the end of the previous video, I said one class actually calculated the rate between 6 and 10 minutes. And I said, oh, I forgot what it was, but it was more. As soon as I got home, I remembered the rate in this time frame was 80 cells per minute compared to the average rate of 37 to 38. And so the question is, why is it higher during this period of time than it is on the average? And of course, the answer is that we are in the exponential period of the growth curve there. So I just wanted to clarify that. Okay, so our next topic is staying alive, and we'll just quickly review the survivorship curves, which give us a little insight about, at which times in an organism's life is death going to be more common. So when you look at a type 1 survivorship curve, we're going to see that survivorship is pretty high from birth throughout the lifespan, and then death rate is probably going to increase towards the end of the lifespan. Remember that a type 1 curve is usually describing a K strategist. So the parents are there to nourish the baby and take care of it and protect it from predators and harm. And then as we go into adult life, most of us are going to make it to a healthy old age. And then at the end, the reason that we end up dying is something like disease. As we are the predators in the ecosystem and we're the large organisms. And so that is your type 1 survivorship curve. Type 3 is the exact opposite, where we see that there is a high infant mortality rate. A lot of the babies that are produced die, and then those who do survive, just a very slim portion, will make it to the maximum percentage of lifespan that is genetically predetermined. And remembering that your type 3 organisms are typically prey items, they're small organisms, and so their environment is unstable, as we discussed, versus this very stable environment of the K strategist. Then we discussed the type 2 survivorship curve, like the squirrel here. Really, his chance of dying could come at any time in his life, just depending what's going on that particular day. It could be a young squirrel being eaten by a predator. It could be, an adult squirrel being eaten by a predator. It could be an older squirrel dying of old age or disease. So these are your survivorship curves. And although it's a different relationship or a different concept than R versus K, you can see how it's very tightly intertwined with that. So we have type 1, low infant mortality and characteristic of a K strategist. Type 2, chance of dying, could happen at any time during the lifespan. And type 3 has high infant mortality. And we're talking about R strategists. Again, don't forget that we're talking about survival. So if this is low infant mortality, we're talking about high infant survival. And if we're talking about high infant mortality, we're talking about low infant survival. Okay. Then we went on to talk about competition. And one takeaway is that when two organisms share a niche and they're competing for resources, if they don't partition the niche, if they are sharing the exact same resource, one of them is going to be outcompeted and the other one will emerge the victor. And that's exactly what we see in these graphs right here. We have the two species of Paramecium, Paramecium aurelia, whose carrying capacity is higher at about 105. And we have another species of Paramecium, Paramecium caudatum, whose carrying capacity in that environment is about 64. And so each, while cultured alone in a tube, does well. Each of them reaches carrying capacity in a similar number of days, so they behave similarly because they are sharing the same niche. However, when you mix each species with the other one, we see some very different results. In Paramecium caudatum, when we mix in Paramecium aurelia, the other species, what we see is that caudatum begins to decline and eventually dies out as it suffers the effects of competition. As we mix Paramecium aurelia with Paramecium caudatum, it doesn't really seem to phase Aurelia as much. It still gets very close to its carrying capacity. It takes a little bit longer, but it doesn't decline and it doesn't die out completely. So, I mean, we can infer here that Aurelia is a much better competitor than Caudatum. So once again, we've reviewed the concept that if you share the same niche, you better be ready to fight, because one of you is going to actually dominate that niche and the other one will be outcompeted. We talked about niche partitioning, how organisms can divide up a niche into different ways so that they can occupy the same niche yet still coexist. And that might be hunting during the day for one species and hunting during the night for the other species that uses that particular resource. It might be living in different parts of the tree, like amongst the branches versus at the tips, or at the top of the tree versus the bottom of the tree. It's the same resource, the tree, or the food sources, whatever it might be. They're just using them in different ways so that they can coexist, and that is called niche partitioning. And again, it's the kind solution to getting outcompeted, right? Rather than being knocked out completely, hey, let's just cooperate. Let's find a way to make this work. And then our last thing on this particular day was how limiting factors, which limit the size of a population, can be active based on whether they are dependent of density, independent of density, excuse me, or whether they're dependent on the density. For instance, things that are density dependent, you're going to see a greater impact when the population increases in size. And I think on your predator-prey simulation, there was a question and it said, when are the effects of predation most dominant? And I think your answer was when the population is large and dense. So there you go. The more predators, the more we're going to see the effects of predation. And like I mentioned, if you were a kid who turned up your predator success and aggressiveness to a really high value, you could see probably how you would knock out that prey population very quickly. If there were fewer predators, then we would see less impact on the population size. Food availability is dependent on the density. The more individuals, the more food they will need. So obviously, if food becomes scarce, we're going to see it have greater impact when the population is very large. It's going to kill more individuals because there's less food for more people. Whereas if it were a smaller population, food availability wouldn't be as much of an issue because there are fewer mouths to feed. And so while there could be some food scarcity, it wouldn't be as extreme. And like we already mentioned, just being around a lot of individuals, whether it's animals or plants or whatever, that's going to increase the spread of a disease. Okay, and so remember, your density-dependent factors are typically some sort of biotic factor, something that's alive, producers and consumers, predators themselves, the pathogens such as bacteria, fungi, protozoans. And then density-independent is going to be something that limits a population size no matter what size it is, right? So a hurricane or a tornado can come in and devastate a population of plants, for instance. And it wouldn't have mattered if there were 10 plants or 20 plants. That tornado was still going to come in, right? Now, these things are usually abiotic and non-living. And so that's the difference between density-independent and density-dependent limiting factors.